So last time we started talking about timing, and we're going to continue that today. The reason we talk about timing is that it's related to delay and performance is one of our three main design criteria. We talk about cost, performance, and energy. So this section is all about timing. And the kind of a key thing, it's just going to switch ahead here. One of the key things is to determine the maximum clock frequency that a design could run at, because the performance is going to be related to the maximum clock frequency. And so we went back to this sort of general model for digital systems, which shows them as a collection of combinational logic blocks, state registers, and inputs and outputs. And for every path, and what happens on every clock cycle, we load a register from values that come from the combinational logic blocks through possibly from the inputs, possibly from other registers. But you can think of it on every clock period as we're transferring data from one register to another, and in the process of transferring it, it goes through a combinational logic block. So we need to allow enough time in each clock cycle to allow that transfer to happen. So the clock period has to be greater than or equal to the time to get the signal out of the register, and that's the clock to Q delay, the time to go through a combinational logic block, and the time to set up to get to the next register sufficiently early so it's ready to be loaded in. Today, a little later, we'll talk about the origin of those two delays, the delays associated with flip-flops. Right? First, we're going to talk more about the delay associated with combinational logic blocks. Okay. And this has to be true for every path in our design in order for the design to work correctly. So if the design is failing because it's failing to meet the timing constraint, right, what will happen is there won't be enough time for the signals to get to where they need to be. And that could be fixed by either slowing down the clock, allowing a longer clock period, or by doing something about the delay, shortening the delay paths. Okay, so that's about timing optimization, is shortening the delay path so we can increase the clock frequency. Okay, so let me just skip some of this back to kind of where we were last time. All right, so we were looking at what is the origin of logic delay, the delay in the logic blocks. And I showed you this kind of cartoon to give you intuition about where delay comes from in CMOS circuits. And I said the right analogy is to think about when you have a logic gate, and in this case it's just a simple inverter. We'll look at more complicated logic gates in a little bit, or next time. When you have a simple inverter, if we put the input to logic 0, which is 0 volts, the p-type transistor turns on, and we charge up the output capacitance. And charging up the output capacitance is kind of like filling up a bucket of water. If you think of water molecules as charge particles and the flowing of water like current, there is a current that flows from VDD through that transistor, and the capacitor is kind of like that bucket, right? So you fill it up, and the water level kind of represents the voltage. So this will kind of fill up like this, and eventually this voltage will reach that one, and it'll stop getting charged up. Right? Likewise, for discharging, it's kind of like dumping the water out of the bucket. Okay. So that's the right model. We're just moving charge particles around. If we look in detail, previously we talked about modeling transistors as resistors. And the reason we do that is then we can have a simple analysis of the charging and discharging time for logic gates. Right. So for instance, in this second one here, when we're going from high to low, we can model this inverter as shown here with, there's input capacitance, right, and that's the capacitance associated with the gate terminals of the two transistors. Remember, there will be a p-type transistor here and an n-type transistor down here. And then there's some here is called CL, which is some load capacitance. This represents what the inverter is connecting to. It's connecting to, there's some internal capacitance here, but there's also capacitance on the wire, as we'll see, and there's capacitance associated with the other logic gates that it's connected to. Okay. But for now, we just call it C sub L, or C, and we have the resistance of the on transistor here. And remember, we said it's not exactly like a resistor, but we approximate it as a resistor. Because if we do, then it's a simple RC circuit. You can write the differential equation for this, and if you solve it, you get that the voltage as a function of time is the initial voltage times e to the minus t over RC, where R is this R and C is this C, right? That's for discharging. So it just exponentially goes down towards 0. Now, to kind of define what the rise, so this is the falling time for the out. We call this the fall time. There's also rise time, which is going up. There's a special, we say time, tau 1/2 or t 1/2. That's the time that it takes for the signal to get halfway from VDD down to ground. Okay. And you'll see why that's an important number later, but we like to characterize the circuit according to its t 1/2. And we can get that by setting in here V equal to VDD over 2 and solving for t. And you get this log base 2 of times RC. And log base, natural log of, sorry, not log base 2, natural log of 2 is 0.69. So we define, by definition, the high to low propagation delay for this circuit is defined to be the t 1/2 time, and the t 1/2 time is 0.69 times RC, right? So it's the R associated with the N-type transistor here and the C of at the output. Okay. All right, we'll do a little more of that in a while, but for now you should just understand that we have these kind of exponentials for charging and discharging. Now, so what that tells us is it takes some time to switch the output of a logic gate. You can't switch it instantaneously because you have to charge or discharge the capacitor through the resistance of the transistor. So how does this give rise to gate delay? Well, I'll show you that with this cascade. So if we take 3 inverters here, as shown in this diagram, and let's assume initially the voltage on these nodes, we have a 0 there and a 1 here, and a 0 at that node, and a 1 there at the output of inverter 3. And then at some point in time, we switch the input to the first inverter from, I'm sorry, we're starting at 1, 0, 1, 0, and we're going to switch it to 0. We'd expect the output of that inverter then to go to a 1, and then the output of that inverter to go to a 0, and the output of the third inverter to go down to a 1. All right. So how would that look if we plot that in time? Well, it's going to go like this, where the first inverter output is going from 0 to 1, so it's going to exponentially rise up towards VDD. Now, when it gets to about VDD over 2, this second inverter will start switching. Right? The reason nothing really happens at the output of this while the output of inverter 2, while the input to inverter 2 is changing because of the nonlinearity of the inverter. Remember, we talked about the fact that the logic gates have this nonlinear transfer function. So the input's going from 0 to 1. The output of this inverter isn't going to change much. It's going to stay very much close to VDD, like as I've shown here. Right? Only until we get to this kind of inflection point, which is around VDD over 2, then the input now will be interpreted instead of as a 0, but as a 1, which will push us into this regime and effectively turn on this N-type transistor, which will start discharging that. And that's that discharge. And when that gets about halfway, then the next one will turn on the P around that point, and then the P-type transistor of that inverter will start charging that up. Right. So that's why we define this T 1/2. We define the logic delay, the rise time or the fall time to be the time that it takes for the output to get halfway from 0 to VDD or from VDD down to 0, because that's when the next, because of the nonlinearity of these logic gates, that's when the next one will kind of switch. So it's a nice property due to this nonlinearity, because then these are kind of decoupled. The first one switches as output, then the next one switches as output, then the next one switches as output. Right? It's not exactly true if you look at it in detail, because this is not exactly flat up here. The transistors turn on a little bit, but by and large, the first order, it looks like what I've shown you here. It's close enough. The other thing about this is, if you look at the time from the input to a logic gate, or an inverter in this case, being VDD over 2, to its output being VDD over 2, that is what we call the propagation delay for that gate. Right? So the propagation delay for inverter 2, this one, is shown right here, because that's when its input is halfway and its output is halfway. And then the next one is here. Its input, inverter 3, its input is halfway there, and its output is halfway there. So that's the propagation delay of an inverter 2 here, 3 here, and this is 2 and 3 in series. So the nice property falls out of this, that the propagation delay through a cascade of logic gates is equal to the sum of the individual propagation delays. Right? So that makes analysis simple. You just kind of add them up. Okay? So that's how rise time and fall time gets turned into gate delay. Now, that's kind of what happens, the physics of what happened. The analysis in real situations is more complicated, because you have to consider the context of the logic gate. In this drawing here, I have a NAND gate. Right, here's the two p-type pull-ups, and that should be no bubble there, but imagine that's the n-type. And we're switching this output node. So everything that connects to the output of the logic gate contributes to the capacitance. Right? So, and I've drawn these little capacitors in here to show you. Every transistor source and drain region has capacitance associated with it. The gate region of a transistor has capacitance associated with it. The wires have capacitance associated with it. So all that capacitance has to be charged and discharged. Right? Additionally, the wires can contribute their own intrinsic delay, as I'll talk about in a minute. They're capacitors, but they're also resistors. So they have their own RC sometimes associated with the wires, and sometimes that's significant as well. So there's a lot of capacitance around, and it's very much dependent on the layout, exactly what it is. Right? So sometimes we just kind of lump it all together and model it as C sub L or something like that. Okay. I mentioned the wires contributing to delay. Let me talk about wires in more detail right now. So wire delay. So ideally, wires are like transmission lines. If you know transmission lines, you put a disturbance on transmission line and it moves through the wire to the other end. So if we change the voltage, let's say at this point, change the voltage at that point from high to low, that wavefront kind of moves down the wire and eventually makes it to the other side. And this propagation is happening at the speed of light. Right? Well, close to the speed of light. It's a little bit different on silicon. But it's approximately 1 foot per nanosecond is the rate at which it's moving. So in 1 nanosecond, this disturbance, it's the same thing in the air or on a wire, it moves about a foot. A foot is really big compared to chips. Right? So what happens, this, by the way, the time from the source to destination is called the transit time. It's the time for the signal to transit along the wire. In ICs, most of the wires are short. In fact, they're much, much shorter than a foot. So what happens is the transit times are relatively short compared to the rise and fall times. Right? So think of the wire. The wire also has some capacitance, and it's being discharged or charged up by the resistance of the transistors in that logic gate. while the logic gate is moving that signal, the voltage on that line up or down, this reflection is going, but the reflection is the transit times are very short. In fact, it reflects and comes back while the node is being voltage on the node is being changed. So we don't even notice this kind of transit time. The wires are too short. The transit times are extremely short. So that doesn't, speed of light delay doesn't contribute to the delay on wires and ICs. It does if we have like Ethernet that goes from this side of campus over to another side of campus, and you might have a few hundred nanoseconds that actually contribute. But on ICs, this type of delay, speed of light delays, are not important. The things that are important have more to do with the capacitance and the resistance of the wire. Okay, so let me talk more about that. Now, if we look at a wire in cross-section across the chip, there's the substrate here, which is typically grounded or connected to VDD, depending on which part of the chip, but it's one of the rails. Then there's silicon dioxide. Remember, we use silicon dioxide as an insulator. And then there's wire. The wire typically these days is copper in most of our ICs. Used to be aluminum, but now we use copper. So it's a good conductor. But there's a sandwich here where we put some voltage on the wire there, and you got this ground plane beneath it. It acts like a parallel plate capacitor. Right? And where the capacitance of a parallel plate capacitor is proportional to the area of the two plates and the distance between the two plates. Right? So the area for a wire is its width of the wire and its length. So this is some wire that's running across the surface of the chip. It's going to have some length. It's going to have some width. From that, we could calculate, and we know what that thickness is, and we know the dielectric constant for silicon dioxide. We could figure out what the capacitance of that wire is. All right. Doesn't matter what the exact value is right now, but just believe me, there's capacitance there. The other thing is that wires have some finite resistance. It's copper. Copper is not a perfect conductor. It has its resistance as well. So a typical model, a way to model a wire would be like this, with small pieces of RCs, right? This is the right model. If you take this, each piece smaller and smaller to the limit, you would get a continuous RC, but it's hard to think about continuous RC, so we think about lots of discrete RCs. So this is kind of the R per unit length. Consider each piece here as a unit length piece. So we have R per unit length and C per unit length. Right? Now, think about the dynamics of this then. You have, if you put a voltage source here and try to change, what we're trying to do is change the voltage of that side. We're sending a signal along the wire. That means we're going to change the voltage here by, let's say, connecting this up to VDD. And we like to get that 1 all the way to this side. How is that going to go? Well, you have to charge up that capacitance through this resistor. And then you have to charge up that through 2 resistors. Then you have to charge up that through 3 resistors, et cetera, et cetera. So you get this, the delta T, the time that it takes to charge up this final capacitor here is going to be RC plus 2RC, right, plus 3RC plus 4RC, et cetera, all the way up to NRC. This is like 1 plus 2 plus 3 plus 4 plus 5. That converges. That's a geometric series that converges to what? N squared plus N over 2. So that means the delay is proportional to the square of the length of the wire, or the number of sections, right? Which is kind of a funny thing. So the longer you make the wire, the much slower it gets just to get a signal through it. Remember here, the R is resistance per unit length and C is capacitance per unit length. And so we get delta T is proportional RC times L squared, the length of the wire squared. It's kind of an unfortunate thing about ICs. It's because then if we have a very long wire that goes all the way across the chip, it's going to take a really long time to get the signal through that wire. By the way, if you into you may remember this kind of effect is like the diffusion. It's like a heat diffusion equation. It's the same differential equation that describes this phenomena. It's just like heat, the same way that heat moves through a solid. Okay, so let's keep going with wires, though. Okay, so in most cases, transmission line effect is negligible, but wires have R's and C. I said this, that the time constant is proportional to the square of the length of the wire. So, but for short wires, like wires that connect between logic gates or connect the output of some register to some logic gates, those wires are relatively short and the resistance is not significant compared to the resistance of the transistors themselves. Right? The resistance in transistors is probably around 1,000 ohms, maybe a few hundred ohms, something like that. The resistance in a short wire is probably in a few ohms. So usually we can just ignore that. Okay. So it's dominated by the resistance of the transistor, so we can treat those short wires just like capacitors. Right? So you don't get this squared effect. You do, but it's a really small term. Right? The predominant effect is going to be R of the transistor times the C of the wire. In this case, by the way, if you look at a densely laid out IC with lots of logic gates and flip-flops and stuff, about half of the C capacitance of a gate load is in the wires themselves. Right? And the other half is roughly in the capacitance associated with the transistors, drains, and the inputs to the other logic gates. For long wires, however, and we do have some critical long wires. For buses, microprocessors, you have buses that carry signals from the cache, maybe up to the processor data path. You have clock lines that are long because they go everywhere on the chip to distribute the clock signal. Or global control signals like a reset signal that connects to every flip-flop, right? Those are wires that go a long distance. Those, because they're long, the resistance builds up, right? Because resistance in wires, I don't know if I said, putting each little piece of wire has some resistance, but if you put a lot of them in series, like in a long wire, then that resistance accumulates, right? So in those cases, the resistance is significant, therefore the RC effect dominates, right? And so this is something we have to deal with. If you made wires that go all the way across the chip, you could not get a signal through that wire within 1 clock period, because these chips are running at very high speed. So you have to do something to reduce the delay on long wires, and we use a rebuffering technique typically is used to mitigate that long delay. And I'll show you how that works in a minute. Before that, though, I want to say for long wires on ICs with high currents, then inductive effect also comes into play. Wires have self-inductance. The inductance is relatively small, but if the currents are high, you can see the effect of inductance. We will look at that later when we talk about power and ground distribution. For now, we'll just ignore the inductance. Okay, so here's the idea about rebuffering. Okay, so for long wires, like buses, control lines, global control signals, clock lines, resistance is significant, therefore the RCL squared effect dominates, right? But what we can do is take this long wire and cut it into pieces and put buffers in here. And these buffers, you could view this as just a pair of inverters, one inverter after another, right? And it doesn't have any logic function. It's just there to provide connection, kind of break up the wire. We could make buffers like this. But typically what you'll do, if you're going to have an even number of them on a wire, put an inverter here and then another inverter here. All right? So then by the time you get to the end of the wire, the signal's not inverted. And what this does, so here's the unbuffered wire. I say the delay is proportional to L squared. as I said before. If we cut this wire into sections, you can see what happens then, that the total delay on the wire is going to be n times L divided by n, if it's n sections. So L divided by n squared, right? And you have n of those sections, plus the delay of the buffers themselves. And you'll have n minus 1 buffers, let's say, in this, if you have cut it into n sections. Right? As we'll see, the buffer delay itself is pretty small, right? So then, if we assume that's negligible for a minute, then you can see then that we get L squared divided by n squared, L over n squared, so it's L squared divided by n, this term. So the delay ends up being proportional to n times less than it was before. So if we just cut the wire in half, all of a sudden the delay is half of what it was before. So that's the usual thing. So essentially you're just isolating the sections of wire where the delay grows with the square and making sure no one wire gets too long. And this comes at the cost of some extra circuitry, but this is what you have to do. I wanted to go back here and say one thing I wanted to say before that I didn't. So these capacitors, we're going to look at the capacitance in more detail, but there's a gate, there's capacitance associated with the gate of a transistor, both types. And with the drains, these are the drain regions of these transistors, and they have their capacitance too. That kind of contributes to the output capacitance of the gate in a way. There's also capacitance associated with the source nodes, like here and here. But the source nodes of both the N's and the P's are connected to the power rails. So what that does is contribute to the capacitance of the power connection here, which is actually a beneficial thing because it tends to stabilize or filter out any noise that's on the power supply. We'll see this later when we talk more about power distribution. Right? You can think of it as little local capacitors here are local places to store charge. So when the transistor turns on and tries to draw some current from the power supply, it can drain its local capacitance first. So it doesn't have to put as much of a demand on the wires that are leading to the logic gates. Right? It tends to make all the signals smoother and less noisy. We'll see more about that later. Okay, so that was wires for now. We're going to visit wires again in a little while. I want to talk about flip-flops because flip-flops also contribute to the delay. We said that within a clock period, you have to get out of a flip-flop, through the logic block, into another flip-flop. And all has to happen within one clock period. But the flip-flops have some delay associated with them. And they eat into the time budget, right? Because here's some place, this is some processor design, and there's an ALU here in the processor. And this is similar to what your RISC-V processor will look like if you take it in the lab. And somewhere in here you'll have a pipeline stage, a stage. There's a register, goes through the ALU and the result goes into another register. Right? This would be kind of a typical stage of logic you'd see, or pipeline stage you'd see inside a processor. In fact, I picked this one here with the ALU because often the ALU is one of the longest paths anywhere in the design. Because if it's a 64-bit processor, it takes a lot of logic gates to go through in order to add 64-bit numbers together. So there's a chance that could be one of the critical paths, or the critical path for your design. Right. So here it's shown up here. We have a register. You've got to get all the way through the combinational logic and get the signal set up here at the next register, all within one clock period. And that's kind of shown here. So the remaining, if you you have the clock to cue time here when the signal comes out of the first register. And then you have the setup requirement for the second register on the right. And the remaining time here, that's, in this example, that's the budget, the time budget that we have for the ALU. So we'd have to design our ALU to fit so that its delay will fit in within that amount of time. In a few weeks, we'll talk about how to design adders and ALUs so that they're fast, right? So we know how to do that. For now, I want to talk about where the delay of the registers comes from. Right? And this is the old formula before. Okay. So in order to understand those delays, we have to look at the schematic at the transistor level for the flip-flops, because flip-flops make up our registers. Remember, it had two latches in a typical CMOS flip-flop. There's the sampling circuit here, and there's a holding circuit here. This is my hand-drawn representation of the delays associated with the flip-flops. There's the clock to cue time, which says when the clock changes, there's a little delay between when the clock changes until the output changes, which is right here. So this delay from clock edge to output changing is called clock to cue delay. And then there's a constraint that says the input signal has to be stable before the clock edge by some amount, and that amount is called the setup time. Okay. There's also the hold time, which we're going to ignore for now because it doesn't come into the discussion, which says how long the input signal has to be held after the clock signal changes. So we're interested in asking the question, what's the origin of the setup time and the origin of the hold time? Well, if you recall, the way that these circuits work is that it kind of works in two parts. When the clock is low, this latch is holding the value of the flip-flop and presenting it at the output, Q, because these are in a ring. This stage is transparent, meaning its input just comes out to the output and there's no feedback. Right? And then when the clock goes to high, they kind of... So what's happening during this period is that the first stage is kind of capturing the new value. Right? It's coming in, waiting for the clock edge, right? Because the clock is at 0. And while this is holding the previous value. Right when the clock goes to 1, just shown here, this one closes its feedback, so it's now captured. This one gets transparent, and then it just gets passed through to the output. Right, so that's just to remind you how the flip-flop works. And how does this associate to the clock to cue? Well, the clock to cue time is when the clock goes to 1, right? And this one closes its loop, and then this becomes transparent. It's just the clock to cue is the time that it takes for the signal to then propagate from this point out to Q. It's got to get through that pair of inverters, and it's got to charge or discharge with whatever capacitance is associated with this node. Right? And the actual time that it takes depends on what this is connected to. If it's connected to a lot of other things, right, then it's going to take a longer time for the signal to rise, right, because there'll be more capacitance here. Right? So the clock to cue can be dependent on what the load is here. So that's the clock to cue. The setup time is just the time that it takes for when the clock is low for the signal to get through these ready to the point so that when the feedback loop is closed, the signal comes back around and reinforces itself. Right? So the signal has to come early enough before the rising edge of the clock to make it through both those inverters. Right? And that's what defines the setup time. So typically for this type of latch then, or this type of flip-flop, setup time and hold time, if you forget about the fan out here, the setup time and the clock to cue time should be comparable, similar to one another. Okay. Any questions so far? Comments? Okay. So back to this timing analysis. We're looking at this. So as I said, there's a lot of paths in this design. Right? There's a path from here to here, path from here to here, path from here to here. Other paths. Here's a feedback path from this register through all that, back through all the way into that register. Right? So there's a bunch of paths to be enumerated and figure out which one has the longest delay. Okay, some path somewhere in the design has the longest delay, and that's what we call the critical path. So I'm going to summarize what contributes, and the path kind of looks like this. So what contributes to the logic delay in that path? We talked about the flip-flop delay, but the combinational path delay has a few components to it. One is how many levels of logic, right? So if you go through more levels of logic, obviously you have more delay. There's the delay of the internal cells. So in a FPGA, these could be the logic blocks. In ASIC, these would be the standard cells. Right? Each one has its own internal delay. There's the delay of the wires. Right? There's input capacitance of the cells also determines the delay, because that determines how much each cell has to, how much capacitance each cell sees, right? And the cell, likewise, the cell fan out. Here you can see this cell fans out to two others. Therefore, this one's going to see more capacitance at its output. Right? And then the transistors inside these logic blocks help determine what the logic delay is too, because if the transistors are wider, they're able to provide more current, more charge per unit time, and therefore their rise and fall times would be smaller for wider transistors. Right? Right. So there's all these components to logic delay, and some of it is under control of the designer, and some of it is given to you by the tools. And what I mean by that is, if you look at the 6 elements of logic delay, and in this chart I show what you as a designer can control and what are kind of controlled by the foundry, right? What are controlled by the library developer who designs the cells, and what of it is controlled by the CAD tools that generates the layout for you. Right? So as you can see, most of these things are under the control of the process or the library or the CAD tools. You as a designer, well, you can control the number of levels of logic by choosing the circuit topology. Right? For instance, we're going to talk about different adders. Some adders have more levels of logic. Right? Other adders have fewer levels of logic. The ones with fewer levels of logic will have less logic delay. Right? So that's one piece of control you have. And the way you write your Verilog, you can adjust, or you can indirectly control the levels of logic. The wire delay is related to the layout. So if you have control on where you put the pieces of your circuit relative to one another, right, you can control some of the wire delay. Now, in FPGA and a standard cell tools for ASICs, you don't really have fine control over the placement of every cell. You do, but you don't want it because it would be too much work. But if you have big blocks, putting a cache close to the data path of your processor, for instance, to keep those wires short, that can help you kind of minimize the delay associated with the wires. And then the cell fan out, you also have some control over, again, by the way that you write the Verilog, the topology of the logic circuit that you design. Okay, so as a designer, there's a process that you go through called timing closure, and that's searching for and beating down the critical path. Right? Timing optimization has to do with finding the slowest path and making it shorter somehow, or speeding up that path. Right? So you kind of look around. So you do this with the help of tools. You have to consider all the connected register pairs, paths, plus input and out, inputs to register, plus registers to output, as I mentioned before. The design tools help in the search. So the synthesis tools will work to meet some clock constraint. So when you synthesize a circuit, you can tell it what the target clock frequency is, and it will try to manipulate your circuit to change its structure in a way that it will get the path delay to fit within your constraint, right? And it will give you a report on the delay on all the paths. There's also special timing analyzer tools that will take your design and report to you what the delay actually is. Right? And there's also simulate. So this is statically. What this will do is just trace through your circuit, kind of adding up the delay along the path. You can also use simulators that can also help you simulate a particular clock frequency and make sure everything is okay. So let me show you kind of what happens in the real world when you're doing timing closure or timing analysis. This is kind of an old example, but it makes the point. This is from a IBM microprocessor. And what this shows is a histograph of late mode timing checks. Okay, so these are timing checks at some point during the design process. And it shows timing slack. And what timing slack is the amount of extra time on a particular path for a given clock period. Right. So this says, and what we're showing here is how many different paths have how much timing slack. So for instance here, 200 at this number, which is about 170 paths, combinational paths, have 240 picoseconds of slack, meaning those paths are shorter than the clock period by that amount. Right? So all these are successful. Right? These have very little. In fact, if you get to 0, that means the delay on the path, along with the register delays, is exactly the clock period. Right? Yep.
Do you know how long the clock period is for this graph?
For this, I don't.
Is it on the order of like a nanosecond? Or?
Yeah, this was probably around a gigahertz processor. So you can see that this is like a quarter of the clock period. So this is late. They've already done a bunch of, if you do, initially you'll get a much wider variance. But later on in the design process, you start speeding up one path and slowing down other paths and getting them to be more balanced. Ideally, every path would have the same delay. That would be optimal design. You never really get to that. You have a few critical paths. In this, okay, so most paths have hundreds of picoseconds to spare out of, let's say a nanosecond. The critical path is here. This is the path that's the longest. It has negative slack, which means it's going to not meet the timing constraint. Right? It takes longer than the clock period. So that's bad. So at this point in the design process, the design isn't running at the speed that it should be. So the designer will go and focus on this path, change the circuit somehow. Right? For you, it would mean probably change your Verilog, maybe put a register, cut that combinational logic into 2 pieces, put a register if you can, add a pipeline stage, move some registers around. I'll show you how to move registers around a little later. Right? And then fix that path. And then the next one will be the critical path. And you kind of keep fixing one at a time until you get to the point where they all meet timing. All right. So, so what can you do in practice again? Well, you can choose, if you have a problem to solve, you can choose the algorithm, and different algorithms that lead to different timing behaviors. You can choose the microarchitecture, kind of a block diagram, right? And that, of course, leads to different timing behavior. The way you describe your HDL description of the combinational logic blocks can affect the number of levels of logic. Where you put the registers in the memory is a big one. Right? I'll talk about that more in a minute. Because really, you have a lot of combinational logic. You can split it up and put registers in the middle of it to break it into pieces. And that's called pipelining, and that's a very powerful technique that we can use. And we can move the registers around to get the paths to be more balanced. And as I mentioned, overall floor planning and relative placement of the blocks can have an effect on the timing as well. Okay, so I mentioned now moving registers around to help with timing, and there's a common operation called retiming or register rebalancing. And I'm showing you here in principle how it works, and I'll give you a bigger example in a minute. Here's a representation of a circuit where the round circles here are logic blocks or logic delays. They're logic blocks, and the delays are in here. So this is a delay of 1 that has a delay of 2. Just some units. Doesn't matter what it is. You can imagine it's picoseconds or nanoseconds. And you see where the registers are. And this is the structure of our circuit. And we like to find a way to speed this up. The critical path in this is 5. If you just ignore the register delays for now, the flip-flop delays, has a critical path of 5. It's this path here. 1 plus 2 plus 2 is 5. This path here, by the way, comes around, has a path delay of 4. So that's not the critical one. This is a more critical one. So we'd like to can we find a way to make it, to shorten the critical path? We can do that by moving the register. In this case, we can add, so we take this register and push it through that logic block. When we push it through, we have to put a register at its outputs, right, to make sure that the circuit still has the same behavior, input to output. Right? But internally, it's going to change timing a little bit. So we move that register from here, put 1 there and 1 there. Circuit still has the same operation. It will still operate the same input to output, right? But after retiming it, now the critical path of 4 here, and this critical path from the output of that register back around here, back to the input of that register or to the input of that register, they're both the same. That will be a path of 4. Right? So we're able to move the registers, rebalance the delays, and the critical path went from 5 to 4, so the circuit will have sped up by, whatever it is, 25% or so. Right. And that's the idea behind register or retiming. The logic synthesis tools will try to do this for you in simple cases, right? But there's many cases that it won't do that. So it's best to think about this in your own designs for yourself, and don't just leave it to the tools. Let me give you another example, a slightly more complicated example. And this time we're going to include the flip-flop delays. Here's a made-up circuit, and I put the delays of these logic elements, the logic gates in this case, in the inside. These are in picoseconds. There's a clock to Q for the registers are all the same. Let's call it 10 picoseconds. And the setup time for register is 20 picoseconds. The critical path I've shown here in red. So it's from this register through that, through that, through that, through that, to that register here. Similarly, it's the same path delay from that register into that other input here. You can look at the other paths here. Here's a path into there. That's shorter. They're all shorter. Here's a path around this gate from the output of that register through that logic gate back to the, back to the input of that register. That's a short path. That's paths 20 plus 10 plus 20. So the longest one is the one I showed in red. Okay. So because of that, critical path delay is 190. So the maximum clock frequency is going to be 1 over 190, whatever that is. Like, picosec, that would be, I don't know, 20, what is it? 2.5 gigahertz or something. Okay. All right. So, so we'd like to retime this. You could think about retiming it by, so we have the sexter register here at the output on purpose. So we have a register to move around. Right. So we could move the register here, and that would shorten this path delay. Right? If we move this register through that logic gate, we have to register the two inputs so that we have the same behavior of the circuit, same semantics, we say. Right? That would shorten the path by 30, which would be good. Really, what we'd like to do is move it all the way over to here, so then we have 80 here, and then 20 plus 30, another 80. That would be a really nicely balanced design. If we could get this register, and as we move through the gates, we may have to duplicate it, right? Get to this point. But we've got this problem here because of the feedback. We can't put an extra register in the feedback loop like this, because that would change the semantics. The way this is designed is it's expecting this signal to be combined with the signal from last time around. If we put another register in here, then we're going to be combining it with a signal from 2 cycles ago. That would change the behavior. Right. So these loops often cause retiming problems for the tools. They really don't know how to deal with them very well. And some tools would just stop at this point. But we're a little more clever than that. We can figure out a way to do it. What we can do is, or maybe the tool would do this, we can't really retime to that point, but we can retime to this point. So we can capture those two together. So we'll still have not optimal, but a pretty good retiming. Right? So we move the two registers to after the register to after the loop. So if I move the register through here, I have to duplicate it. I have to put it here and here. And then when I move it through here, I'm going to have to put 2 registers here. And we'll have another one up on that path. So that's what I've showed here. Right, so that's what it looks like after we've done it. So now, we haven't changed the functionality of the circuit at all. We just changed the internal timing. Remember, because we had an extra register here, we just moved it around. I didn't add an extra delay to get through the circuit or anything. Right? So if we look at this path now, we have the 10 plus 80 plus the 20 plus the 20. So critical path of 130 versus the 180. So there's definitely an improvement. Now, the tools could get to this point. We can actually go further if we know something about the internal, the reset, the initial value for these registers. If these 2 registers initialize to the same point or reset to the same value, we can combine those, right, and move them into the loop. Okay. So think about what we have here. We have a delay around here, and then we have a delay over to that OR gate here. So we can do all that with one register. If we change the circuit slightly, so we do it this way. So we combine those 2 registers here. So now we still have a delay around the loop, and we still have a delay to that OR gate. And you can do that if those 2 registers have the same initial values. If the 2 registers had different initial values, you can't do that because you need one initial value going this way and one for initializing the loop. But if they initialize, and it's common they'd both be initialized to 0 or to something that's the same. Okay, so we can do that, and we get to this point. Right, so that's nice. And then we can actually push this register. I think I have it annotated here. I don't, but yeah. We can push this register now this way. We'll come out there, and then it will come back around the loop right here, which is what I've done. So that register goes through there. We get it there and there. Right? And now we kind of met our goal of getting a register before the loop. And so now we have critical path of 10 plus 80 plus 20, 110. And this one is going to be 10 plus 20 plus 30 plus 30 plus 20. So that's 60, 80. So they're balanced now. And we get the best case critical path delay of 110. So the clock frequency will go up to whatever is associated with that. So we've made a significant improvement by just moving registers around. So this is a really cool technique because it can give you a big performance improvement with with really no extra cost. We're just taking registers that are already there and moving them around to more optimal spots. Sometimes, as you can see, if you move a register through a gate, you get 2 registers where you had 1 before. Or you move through a logic block, because you have to now, instead of registering the output, you register the inputs, so you may have more registers than you had previously. So it does come at an increased cost. It's the cost of the registers. But usually it's worth it to get extra performance. Okay, so that's the retiming technique, and that's a very popular technique to use, that designers use in order to do timing optimization. It's kind of related to pipelining, which we'll talk about later. And pipelining is the same idea, but you add registers where you didn't have them before. You don't just move them around, you add new registers into the circuit. What that does, pipelining does, is change the input to output relationship. It adds extra delay to get from input to output. But in the process of doing that, you can increase the clock period by having shorter stages of logic. Okay, I made the point about layout. I just wanted to show you a picture of, this was an old microprocessor, and you can see it has the data cache here and the instruction cache, and kind of the data path laid out here with execute unit and control unit. And designers, when they design these kind of chips, particularly processors that are going to be high volume, and you want to get the area as small as possible, so you want to minimize the amount of the chip that is associated with wires. So when there's a lot of wires between blocks, you put those 2 blocks close to one another so that the connections are short, and that helps the timing, and it helps the area, and it helps the power. So having a good layout is a way to optimize all 3, not just the timing. So I think I talked about the timing tools already. Just finally, I wanted to show you this. This is a cell from a standard cell library that is typical of an ASIC standard cell design flow. This is a 3-input NAND, I believe. And this is part of the information that comes with the library. And this is the timing information, this column here. And it shows for each input, there's 3 inputs, the propagation delay for this gate going low to high when the input's going, I guess that's the output going low to high, output going high to low, et cetera, et cetera. And it's this formula here that has some delay plus some number times C, and C is the load capacitance, right? And then it's actually a function also of the rise or the fall time of the input. Right? We're going to ignore that mainly in our analysis. But the thing to remember here is that there's some fixed delay, which is independent of the output capacitance, and then there's some delay that's a function of the output capacitance. Right? So that's the way the cells are modeled in the tools. And so the synthesis tool, when it's trying to figure out how to rearrange your circuit in order to meet timing, it knows what the delay through the logic gates that it's going to map your circuit to is, so then it can, it can make an estimate of what the critical path would be. Same thing, the simulators can use this to simulate your circuit and have a fairly accurate timing. Now, what it doesn't have here is it knows what a logic gate might be connected to 10 other logic gates, so it can compute what the fan-out capacitance would be. It has to make a guess at what the wire capacitance will be until there's a layout that's generated. Right? So early on, during the logic synthesis process, it may just estimate what the wire capacitance will be. Once you push it through all the way to get the layout, then you can take that actual capacitance information from the layout, put it back into the simulator or into the timing analyzer, and do a second pass of analysis with information from the actual layout. That's called back annotation. You take the actual physical layout information and bring it back into the analysis, either static analyzer or into the simulator. Okay, so that was all about kind of high level, what you do as a designer to meet a particular clock maximize your clock frequency. What I want to do now is talk more about how we model gate delay. We roughly talked about how an inverter works, but I want to give you a kind of a more rigorous treatment of analyzing gate, call it transient response, or the actual output changes as a function of input changes. So this is where we were earlier today, where we have, with a simple inverter, that let's say that the propagation delay from high to low at the output is this natural log of 2 times RC, where R is the resistance associated with the N-type device, and all the capacitance that's being switched represented as C sub L. There'd be a similar one for the pull-up, for the rise from low to high. Right? In that case, we'd use the RP, which is the resistance of the P-type transistor. Now, I already mentioned this, but we're kind of taking our simple switch model that we had earlier, and we're going to augment it with some capacitances here. Okay. So I already said that the gate capacitance, we can model that with, here we're going to call it C sub G. In fact, the reason we use this kind of symbol for transistors is to remind us that this is really a capacitor here. This is the way that MOSFETs work. Unlike bipolar transistors, if you studied those, bipolar transistors, in order to switch them, you have to put current into the base region, which is the analogous terminal to the gate. And nice thing about MOS transistors is we say they have high input impedance, meaning once you charge them up, they don't take any more current. Right? You just charge this up, get enough voltage on here, it'll turn on the transistor. But it's a capacitance there, so you have to put some charge there to get the voltage up. Right? There's also capacitance associated with the source and drain regions of the transistor. Right? And then we have the on resistance. Okay, so this is kind of an elaborate, a new, slightly enhanced model for MOSFETs. Again, we're going to just assume that when it's on, it's a resistance. Okay. So here's an interesting question then. What happens if we make the MOSFET W times larger? Remember, I said there's a width associated with the transistor. I'm going to go back to this layout. You can see some transistors here, and here's that's the width here. The current is maybe hard to see here, but the current is flowing through the transistors. Here, they're all in series. This is, I don't know which, this side is the ground connection. That side's the output of the gate, the drain connection. Right? And when it's discharging, all 3 transistors are on, and the current flows through here. And you can see that the width of the transistor, which is this dimension here, it's going to have something to do with the strength or the resistance. The wider it is, the less resistance. Right? The higher the conductance. Okay, so what happens then if we take our transistor model and we make the transistor W times wider? Well, you can see from that picture the gate region, which is the overlap of the polysilicon and the diffusion region, that's going to grow with W. So and think of that as a parallel plate capacitor between the transistor gate and the channel region. That area is going to grow with W. So the capacitance of the gate will go with W, so it's going to be C sub G times W. The source and drain region, the connections on either side of the channel, they're going to grow with W as well. So the drain capacitance and the source capacitance will scale up with W. What happens to the resistance? Well, I said when you make it wider, it's stronger, the resistance goes down. That'll go down by a factor of W. So the resistance goes down by W, the capacitances go up by W when we make it wider. All right. So something to keep in mind, we're going to use that in a few minutes. So if we think about that then in the context of a pull down, Here's a pull-down arrangement, or the N-type transistor. There's the N resistance. And then in this case, we're not connected to anything, right? So it's just the transistor with its own drain capacitance there. And this is the minimal size one. If we size the transistor, this is what our picture is going to look like. We have the W times CG here. That's the gate capacitance. We have the channel resistance of the N-type is now Rn over W. And then the drain capacitance is W times bigger. Okay, so for traditional, I don't know if we mentioned this before, but for traditional CMOS processes, the B types are twice as resistive as the N types for a given W. Right. This is because the mobility of holes is about half of that of electrons in these processes. So for a given width, the P type is twice as resistive. So the transistors aren't really symmetric in that way. So it's a little bit different with FinFETs, and FinFETs are a little more balanced, and different processes are different. But to make things simple for us, we're going to assume for the next little while that P-type transistors are 2 times as resistive as N-type transistors. Okay. So that means if we look at our kind of minimal switch arrangement for pulling up, we're going to have a situation like this. So for a given CG, a given minimal size transistor, right, it's going to have CD of drain capacitance, but its resistance will be 2 times the resistance of the N. Now, if we want the pull up and the pull down, think back to those inverters that I was showing you, the pull up and the pull down transients. If we want the inverter to pull up at the same rate that it pulls down, that has the same delay from low to high as delay from high to low, we'll need to make the P-type transistor twice as wide as the N-type transistor, right? Because it has twice the resistance. Right. So a pull-up arrangement that's sized for symmetry, meaning same pull-up delay as pull-down delay, is going to be twice as wide. So it'll have 2 times CG input capacitance. The R will be the same as the pull-down R. That's what it means to be balanced, as the same pull-up R as pull-down R. Right? But then, since the transistor is twice as wide, it's going to have twice the drain capacitance. In general, if we make it W times bigger, it would look like this. Then we can scale this, keep it sized for symmetry, but make it W times bigger. We'd have 2 times WCG. I'm just putting W here. Here divides the resistance by W, multiplies both capacitances by W. Okay. So now we can look at an inverter. So this is an inverter that's sized for symmetry, meaning it has the same pull-up as it has pull-down strength, same delay pulling up as delay pulling down. Okay. So the resistance of the pull-up and the pull-down, and this is at some size inverter W. Right. So it has same pull-up and pull-down resistance. The C int, this is the internal capacitance, is going to be, we'll get 2W from the pull-up and 1W for the pull-down. So we have a total of 3W CD at internal. This is the 2 drain regions, basically, the internal capacitance. The input capacitance will be the input capacitance of the N-type, which will be CG, or WCG, plus the twice that for the pull-up, because the pull-up, the P-type, is twice as wide. So it would be 2 WCG there, so we get 3 WCG at the input. So that's our inverter model. Now we're going to do one kind of classic thing here, which is we want to get rid of some of these C's so we can get to a nice result. So we're going to define CD to be gamma times C sub g. So gamma is a factor that's related to the process, and it's approximately 1. And it's the factor that relates the unit capacitance of the gate to the drain. And you'll see later why we do this, but we introduce this gamma in here. Once we do that, then we can represent the internal capacitance as 3W gamma CG. Right. And the nice thing about this is now that we only have one type of C, it's CG. We get rid of CDs, and that's why we do it. Okay. Once we do that, then we can write down a formula for the intrinsic delay of the inverter. So this is the delay of the inverter without any load capacitance. Right? The only capacitance we're considering is, for the switching, is its internal capacitance. Right? So this is going to be what? 0.69, because we're going to go halfway. The resistance, which is R over W, times this capacitance, the internal capacitance, which is 3W gamma C sub G. The W's cancel out. So we get this 0.693 times 3 gamma R times C. This is the intrinsic delay of the inverter. It's interestingly independent of size. So if we make really big transistors, as long as we scale the P and the N together, it doesn't change the internal delay of the intrinsic delay of the capacity of the inverter. Now, we're going to move on to the next step. We're going to consider the effect of adding an output capacitance here. All right, so here it is with a load capacitance. So I've just augmented that last picture. I added a load capacitance here. And here's the formula. So it's going to be this 0.69 times the R over W times the C internal plus the C load. Now we have to charge and discharge not just the internal capacitance, but the load capacitance as well. So this represents everything that this thing is connected to. So we do some algebra here. Well, first we replace C int by this 3W gamma C sub G, and then rearrange terms, factor this out, a little more algebra. We get to this point where we have the intrinsic delay of the inverter times 1 plus C sub L over gamma C int, which is kind of nice because if we look at this ratio of capacitance, we define this ratio of the load capacitance CL to the input capacitance of the inverter in this case. So we're looking at the capacitance of this over the capacitance of looking into the input capacitance to the inverter. That's what we call the fan out. To switch of this inverter, you have to charge or discharge a certain amount of capacitance, and then that will go and charge another capacitance on the output for you, right? The fan out is how much sort of gain you get out of this device, right? That's what we call F, so it's that ratio here. And you got gamma in here. So it's this fairly simple formula here where that's the intrinsic delay that I calculated before, right, on the last slide. So it kind of looks like this. You get delay linear proportional to the F, right, with some y-intercept. So if F is 0, we just go back to the intrinsic delay of the inverter. That's the inverter just switching its own output, right? And then as you add more and more output capacitance, the delay will grow linearly with that, as you'd expect, because it's just an R times a C. If you make C bigger, the delay is going to be bigger. So this is the type of model that a lot of the tools will use, simple delay model for logic gates. And as I showed you in the diagram, this information on each logic gate will, from each input, there'll be an intrinsic delay, and then there'll be a fan-out dependent delay. Now, the next step will be to do the same type of analysis for logic gates. And I'm not going to do it now because I want you fresh, be able to follow it. It gets a little bit complicated. But what we're going to do then is derive the formula for gate propagation as a function of fan out F, as with the inverter, but for this circuit. And then we'll do it for the NOR gate, right? We're going to do it in such a way so that the input capacitance into this gate is the same as the input capacitance into the inverter. And this way we can then have a fair comparison between the drive strength of a NAND gate or NOR gate versus the drive strength of an inverter. But I'm going to do that next time. So for now, we'll just kind of leave you with this. This is our simple model for the propagation delay of an inverter. And you can see there's kind of a fixed delay, and then there's a delay that's a component that's a function of the fan out. And it's more or less linear. And we're able to get to this point because of our simple approximation about the transistors acting like resistors. And you know, it's close enough for most applications. So that's it. Any questions? Okay, good. So we'll see you back here on Thursday.